would like to invite Shlomi Boutnaru from Resilient, ex-PayPal, to talk about the fileless attacks against Linux. Welcome.
The second computer, so I can also show the demos. So. Okay, so until the virtual machine will start up, and first of all, I'm happy to be here. I want to start with a personal story. When I was a little boy, I loved magic tricks. And who doesn't love magic tricks? And I think the most interesting part of magic tricks is to understand what is really going on behind the magic itself. Today, I'm going to talk to you about something which I think is magic, how to execute code only from memory without touching disk. Okay. Let's see that everything will start. So a little bit about myself. My name is Shlomi. I was the CTO and co-founder of a company called Cyactiv. Cyactiv was acquired by PayPal in 2015. Today, I'm currently the CTO and co-founder of a new startup company here in Israel called Resilient. I see we have a little bit of a problem with the screen. But basically, the things that I want to talk about is to start with the definition of what is fileless malware. Basically, fileless malware are variants of malicious software which are only memory resident. They are only based in memory. And due to that, you are changing between the. Due to that, they don't have any part of them located on the file system itself, which has the ability to evade different security measures, such as file integrity monitorings and others. If you will see in the news, there are a couple of different events in which those type of fileless attacks have been conducted. Yeah, but that's not a presentation. Yeah, okay. Yeah, if you want, you can go to the presentation here. No, לא זה. אתה יכול לפתוח אחד אחרת. תמצא אותה ואז נחליף. Okay, I will do that if needed without the presentation. Basically, there are a lot of incidents in which fileless malware were part of the attack itself. You can see here a couple of examples, but if you will see the statistic, 77% of attack compromise that were conducted on 2015 included fileless malware. And due to that, fileless malware has become one of the biggest threats of companies today. Do you want me to? I will switch to a different computer. Just a second. Okay. So I won't do that again. But now you can see the different stories that were in the media last year regarding fileless attacks. And now we can see the statistics much better. 77 of attacks that successfully compromised the organization utilized fileless techniques. A third of all attacks are projected to utilize fileless techniques in 2019. And most of the time, when we are seeing fileless attacks, we are seeing them targeting Windows. Here you can see a couple of examples of open source code which utilize which utilizes this type of techniques. You can see things like .NET to JavaScript, a framework that was created by Project Zero, James for sure, that shows how we can load .NET files directly from JavaScript. You can see PowerSploit, a framework that enables us to execute Mimikatz directly from memory without touching disk, and there are many more. So we saw that fileless is something that is going on. We also saw a couple of examples targeting Windows. Now let's show what can we do, how can we leverage those techniques for Linux environments. As you know, Linux is all around us. You can see that in different mobile devices such as Android, which is based on Linux. You can see that on other IoT devices. You can see that in many more devices. And because of that, the issue of using malware for Linux has become one of the biggest threats for the IoT environment. Here you can see a couple of examples of Linux malware starting from the 90s to 2018. Those are only examples, but there are many more. I will try to show a couple of demonstrations, but before that, I want to give you a little bit of an overview about how can we run or how can we execute fileless malware on top of Linux. So basically, in each Linux, we have a command which is called mount that gives us the ability to see the mounting points which are defined on a specific compute. It could be a container, it could be a VM, it could be an IoT device, it doesn't really matter. And here we can see that there are a couple of those mounting points which are based on a file system called tempfs. Tempfs is a file system which all of its content resides in RAM, random access memory, which means that all of the files that you are seeing when you are listing a directory on tempfs are not really backed by a hard drive. Because of that, what we can do is to mount a tempfs file system, include on top of that a new file, and execute it. We will show a demo about that. That's the first thing that we can do. And thus, this technique still has a couple of problems if we are talking about cases in which we want to be evasive. Why? Because tempfs can also employ swap space when physical memory is not enough. And because of that, we can have in our backing store, in our hard drive, still remnants of that specific fileless attack. Because of that, I want to show you and to later also demonstrate a better way of doing that. Not only leveraging tempfs. Also, I want to say that basically, if you will see on the screen here, you can see that there are a couple of tempfs file systems which are default. Here, it's on an Ubuntu machine, that most of them are marked as non-exit. You can see that in the orange on the screen. Non-exit means that you can't execute a file from that specific location. But you can see that not all of them are marked as non-exec. The second one and the last one are not marked as that, and we can leverage that. We will see that in a couple of minutes. So we said that first thing we can maybe leverage tempfs, and we were going to see that. But I want to also tell you about another technique in which we can do that without the need of tempfs. Linux, as any operating system, Windows, QNX, Integrity, VxWorks, and others, embedded, not embedded, has an interface that enables a programmer from user space to execute code which is part of the operating system, which is called, that specific interface is called system calls. Those specific system calls enables the programmer to interact with the hardware without the need of really understanding what is below him. For example, it doesn't really matter for a programmer in Python to understand what is the physical media in which he wants to write a file. If it's a physical hard drive with magnetics, is it an SSD? Is the vendor of the drive Samsung or others? And because of that, there are those specific system calls, the interface that enables the programmer to leverage the operating system. And one of those system calls in Linux is called memfdcreate. You can see that the goal of memfdcreate is to create a file descriptor that describes a file, but not on a hard drive, an SSD, a magnetic drive, doesn't matter, but only in memory. Just to give a little bit of more information, or maybe a little more of history about Auto or knowledge, a file descriptor is a number that is used from user space in order to create or to do some kind of an operation on a resource in the operating system. And FD can be, a file descriptor could be to a file, to a network socket, to a pipe, to a queue, and others. For those who are fluent in Windows, file descriptor is a handle in Windows. And here we can see the description of the specific file system that enables us to create a file descriptor to a file only from memory. Another recap that I want to give you is the way in which processes are being created in Linux. Process creation in Windows is being conducted by calling one function, create process and its variants. In Linux, we need to do that in two steps. The first one, called fork, which duplicates the current process. The second one is called exec, and its other variants that we are going to talk about. And after doing that, we replace the code section of the specific application that we want to do. So for example, when you are using bash and you are, for example, using ls to list the content of a directory, you first fork bash, you have two bashes, and then you have a new ls command. Why do we need to understand that? That's for the demonstration in which we will show how we will create a process from memory-only content. And to do so, we have the fork system call, but we also have the exec system call. The exec system call executes a program pointed by a file name. The file name needs to reside on disk. On the other end, there is another system call called fexecv, which enables us to execute or to change the code section of a specific process only by giving it a file descriptor. So if we will take memfdcreate and put it together with fexecv, we can create something that is executed only for memory. That's overall what we are going to see. So in order to do that, I will try to connect the computer again so we can have the demo. I will move the screen a little bit in case that we won't have the ability to see the entire screen. OK. I will start with a couple of small examples. I'm opening a terminal on Linux. I will basically zoom in a little bit. I hope that you see that very well. Let me do another one. OK. Now, the first thing that I want to do is to go to do, again, the mount command. Here we again see all of the tempfs file systems that are configured in this specific computer. If we will go to /1/user1000, we can see that if we will do, we can see that this specific directory is part of a tempfs file system. And if we will put a file here, for example, let's copy ls, using the backtick in which says where on the file system the file is located, using the backtick says to the interpreter of the shell, first execute what's inside the backtick, and then do the copy command. And let's copy that locally. Here we can see we have a specific file called ls. And if we will try to execute ls, ls is executing. Basically, it doesn't seem very strange, but basically, we are now executing that only for memory. By the way, if we will move that to a different place in tempfs, like as sysfs cgroups, for example, we can see it's non-exit, and it won't be executed. I want to show you another example. So that's the first thing that we can do. The second thing that I want to show you, let's open Python. Python is a programming language which is very known today. And let's try to write some kind of a script. So we will start by importing C types. C types is part of the Python language, which enables us to call code which is outside of Python, which is, for example, compiled in C and C++. And then what we are going to do, we are going to create a reference to the libc library, which I'm going to explain in a couple of seconds. So let's start to do that, and then I will explain. So ctypes.c and DLL, none. C. OK. Now let's put syscall.libc.syscall. And then if we will call syscall.39, we will get a number. OK. What's that number? So basically, what have we done until now? The first thing that we did, syscall equals libc.syscall. When today you are writing a program, you are not writing, or you are not using the system calls directly. You are using some kind of a library that enables you to call those system calls very easily. There are standard C libraries for most of the operating systems. And here what we're doing, we're getting reference to that. One of the functions that reside in libc is a function called syscall, which enables us by passing a specific number to get the specific system call that we want to execute. Every operating system has numbers for specific system calls. Specifically in Linux, on this version, 39 is the number of syscall for the system call which is called getPID, which means give me the process identifier of the current one. So this number is the process identifier of the process which I'm running now, which is Python. If I will open another terminal, now we'll do a couple of zoom ins because I don't know why the Control++ doesn't work, but it's OK. There is nothing better than giving a presentation with surprises. And then we can go to another part of the Linux operating system called proc, which is a part of the operating system that can give us information about running processes. If we go there, and we go to the process number 226, we can see, maps. We can see the memory mapping of the specific process of Python. And you can see that there are different files loaded. For example, you can see that there are different SO which are loaded. SO is shared object. It's like DLL in Windows, but in Linux. Other, you can see the heap and other different memory parts or different files or regions that have been loading to the address space of the specific application. OK. So now, what can we do? We want to leverage the memfdcreate and to execute specific code. So let's do that. Let's call the specific system call, which is number is 319. Let's give it a specific name because a mapping has a name. It doesn't really matter. And let's give it a specific flag that it needs. Sorry. No, it's OK. Let's do that better. Let's call it FD, so we can have something. And let's print FD. So basically, we created an anonymous mapping the file description number that got back to that was number 4. And if we will go again to the information, we can see that we created it twice because on the first time I didn't get I wanted to change to have a better variable name for the FD. So here we can see that we created two new mappings. The 0, 1, and 2 are std in, std out, std error. Here we have something which is called /mmfd.n, and it says that it's deleted. In Linux, we have a command called file, in which we can try to check what a specific file is. And when we are trying to do file on that, we have something which is that the operating system said it's a broken symbolic link. The things that we can do now, if, for example, we will take, we will take ls again, for example, and we will copy that to proc. Let's copy that to 4. Basically, what we did, we took the specific ls command and copied that to 4. If we will do file now, what do you think that we will get? Still a broken symbolic link. But if we will try to read the first part of that, you can see when I do cut on 4 and I read a couple of first lines of that, I can see a magic number. The magic number ELF means that it's an executable. So basically, the things that we can do, we can now do 4, and basically we got ls. We can see that basically the command that was executed, it's ls. But we haven't created any file. Why? Because everything is in memory. If you will go and see the maps, if we go and see the maps of that specific application, we won't see ls because we copied that to something which is in memory. So that's the first step of how can we do that. And of course, here we saw that on a specific computer, but we can enlarge that and do that on for example, on a demo application. Here we have a demo web application in which the code of the application is something like that. You can see that we have some kind of a function that mimics a way in which part of the web application firewalls or other secure mitigations are doing. For example, we have here an application that based on input from a user wants to execute some kind of a Python commands, and because the security administrator here is very afraid, he doesn't want to give the ability to arbitrary command, he says that if in the command we have something like system or OS system that enables us to create a process in Python, so it will write us some kind of an error, and if not, it enables us to execute a command. So if we will go and see the demo, we can start. If we will take this specific line and we'll try to execute that, we will get an error. Why do we get an error? Because we have, as you can see in the URL, we have os.system.ls.something. But if we will go and do something which is a little bit more strange, let's do something like that. We are not putting os.ls there. We are doing something else. We are in Python, you have what is called, you have help, and you have the ability to see what are the functions inside of a specific class. For example, if I do dir.os, let me do import os. If I'll do dir.os, I can see the strings of the functions which are inside OS. Basically, that enables me to write any type of strings that I want in order to bypass regex by doing something like that. If I will take dir.os, the first one, and then the first letter, here is a way in which I can write x without writing X inside of a specific thing. You see that I don't have the appearance of the X capital letter in the command itself, but at the end I get X. And it's something which is part of any Python environment. We have the same things also in PHP and others. So if we will go back to the demo, and if we will run something like that, basically we will get that the command was executed as we wanted. And if we will go to the server itself, you can see that the server basically executed the ls command, because we can see the entire directory listing of the etc directory in which we wanted to do. So what do we have? From the first one, we have the ability in which we saw we can run code directly from memory, or by using tempfs, or by using the trick with memfd create. The second thing, the second capability that we have the ability to bypass regular expression by creating strings in a different way, by leveraging already loaded strings in the environment of the interpreter, which is executing the relevant web server. And now what we can do is to take both of them, as you can see here in the demos, and do all of the things that we said before, only by using the availability of, let me show maybe the code again. Basically, what we have here, at the end, we have an eval row which is being executed. What we want to do is to overcome those ifs. Here we have only a specific if. So we want to run system or os.system without using that specific substring. If we will do that, we will come here. And if we will come here, we can run whatever we want. And basically, what we can do is to leverage those two techniques to execute any system call that we want. For example, the get PID or the create the memfd create, and basically execute any type of code that we want. So that's basically the entire demonstration with the caveats of the computer. Let me go back. So let me go back and maybe give a little recap of the stuff. Basically, what we had a web server running on HTTPS, which had a vulnerability in which we had the ability to overcome the regex in order to create some kind of a code execution. Because the specific web application is based on Python, we had the ability to call directly the system calls, and by that, creating an anonymous file mapping, adding to that information, and then executing the operation that we wanted. That's the second demo that we already saw. And because of that, I want to talk about a couple of things. First of all, I want to explain why this capability enables us to overcome whitelisting. Today, most of the whitelisting capabilities are doing the following. Before the loading of a specific executable, a hash is being computed on the file that is going to be loaded. If the file matches a specific list, or if the file is signed by a trusted third party based on configuration, the process is being loaded. The problem with those specific capabilities is that after the file is loaded, the whitelisting part is over. The only thing that we can have is heuristics or other capabilities. The second thing that I want to talk about is that think about the entire operating system as a Bible. I don't know how much of you are reading the Bible, but there is a difference between Spanish Bible, or in Hebrew it's called Sfaradim and Ashkenazim. The biggest difference is that the Ashkenazim, when they are reading the Bible, they're reading that using a table of context. First, read the blessing on page 4. Then read the blessing on page 5. And basically, they are creating the entire things that they want to read based on different parts. And because of that, their Bible, their Siddur are smaller. And it's basically, if you think about it, it's like rope, like return-oriented programming. And the thing that we can do by leveraging this technique is that we also don't need to send any executable to the victim. Basically, what we can do is to create a file mapping and then copy to memory only the gadgets that we want, which are already in the operating system itself. Because if you think about it, we have thousands of ELF files on the operating system itself. Probably we have all of the gadgets, all of the capabilities that we want. For example, if we want to create a reverse shell, we already have an executable that can redirect standard input-output arrow, can encrypt the configuration, and to send the shell backwards. It's called SSH. If we want to copy files, we have CP. If we want to move file, we have MV. So basically, we have all of the executables already inside of the machine itself. So if we will take the technique that we talked until now, we will create an anonymous file mapping. We will build the target ELF file that we want based on different pieces of files that we already have in our computer. We can create a full-fledged malware with no need to send any file to the victim itself. For example, think about Android. I don't know how much, or I don't know if you know, but Android comes with a built-in screen capture file. It's called screen capture, if I remember correctly. Basically, if you have an ability to execute code on an Android device, you can just copy that part of the screen capture into your anonymous file mapping and take a screenshot. You can also use other applications that are already there. Again, if we are talking about the Android example, if you already have an application that supports video, like Skype or others, or any type of application which is already installed, you can just leverage that. Basically, again, as I said, you can think about it like WAP on steroids. You can get any type of already connected or already installed application on the device, an IoT device, a server, a workstation, doesn't really matter, to build your target malware that has any type of vulnerabilities that you want and execute all of that only from memory. The only thing that you need is to create some kind of an index and to know from which executable you want to copy which part and what's the offset and what's the size. After that, you can do whatever you want. So that's the first thing regarding whitelisting, why whitelisting is not enough. Again, fileless attacks are not relevant only for Windows. We saw different examples of GitHub repositories that have tools of fileless malwares in Windows. Also, if you want, you can go over GitHub and you can see there is a project called NetELF that enables you to execute code directly from memory while only sending that over the network. Here we saw, by the way, an example in which we also don't need to send the executable itself. We just build it on the fly based on code that we already have. A third thing that we saw is technique for bypassing security measures. Basically, and we saw only a small string of doing some kind of contains that the specific command doesn't include system or OS.system. But basically, a lot of security measures are trying to use some kind of regular expressions and other techniques in order to filter or to understand if a command has something malicious. The problem with that is encoding tricks, like the things that we saw, and there are other. I encourage you to see there is a couple of good block write-ups regarding PHP and how to overcome different WAFs of different cloud providers. You can see that in the reference later. Also, we saw that running code from memory can be done in a couple of ways. Not all of the ways are created the same. The first one, in which we leverage TempFS, we still have the danger in which, if we will use a lot of memory, our code can be backed up in the hard drive because of swapping, and then we will touch disk, and we won't be memory only. And the third part that takes all of that is that it's something that can be done from a web application. It's something that can be done as part of a malware implant. It's something that can be that can be done in other examples. Talking about maybe the last example of forensic artifacts. So we talked until now that all of the code was only in memory. But you saw that even if the file was created only in memory, we had a file descriptor. And in proc, in the file descriptor directory, we still had an entry for that. So basically, you can understand that one of the things that you can do from a forensic perspective and an incident response perspective is to do the following. Go over the file descriptor directory of all of the processes that you have, and try to see if the content of those specific file descriptor, if they have an ELF file or an executable file or a script file or something like that, if it's backed up in the hard drive or not. If not, you found something which is only in memory. Of course, you need to do that very carefully because you will have probably sockets and pipes and other stuff in which you need to handle. But basically, we can also see that even if you do only and you run only code from memory, you still have some kind of an artifact. No one, even the greatest hacker, can be a magician. Basically, here we saw the magic. And when you understand what is the magic, you can also understand how to find it. I think that in Enigma 2016, there was a good talk by the chief of the TAO. And he said that basically, one of the biggest advantages of an attacker that he knows the system better than the defender. So I encourage you to understand and live your system better and better. Because basically, even if the attacker has great capability, he can't beat physics. For example, if he created a file descriptor, it needs to be there. Basically, most of the computers that we are talking about today are based on the von Neumann architecture. Something needs to be executed, it needs to be loaded in memory. So analyzing memory, comparing memory to what is going on the file system, to the things that aren't on the file system, is the best way to identify and find this type of threats. Basically, and I will iterate it again and again, at the end, an attacker needs to load something to memory. Maybe it doesn't have a file. Maybe it's not in a socket. Maybe it's not in a pipe. Maybe it's not in, I don't know what type of a resource he's going to use on top of the operating system. But basically, it needs to go to memory. And there is no way to overcome that. And thus, as a defender, as a forensic investigator, as an incident responder, you need to understand that there is gold in memory. There is gold that is just waiting to someone to take it from there. I guess that most of you already know about different frameworks that are leveraging memory. For example, volatility and others. I encourage you, again, use them, check them, find and create new plugins. Support the community with that. I want to finish with something that I think is the most important thing. As you know, security and technology are changing at a rapid pace. Once upon a time, when I was a little boy, my grandfather told me, ensure that every day you will learn at least one new thing. A day you didn't learn anything is a day you wasted. And because of that, I encourage you. Find something interesting from the technology perspective or other thing and learn every day. That's the only way in which you can also combat these type of threats. Think about it like arm wrestling. If one that doesn't go to the gym or doesn't work out will try to fight someone else, he won't succeed. The gym in the technology space is learning. As much as you will know, you will have the advantage. So ensure that you won't waste any day in your life and thus learn something new every day. I hope that at least one thing you learned during this presentation, and I helped you so that you won't waste your day. And again, sorry for the technicalities, but There is no better thing to give a presentation with a couple of hitchhikes or a couple of problems, and of course to be the one before lunch, which is always very, very challenging. So thank you very much. If you have any more questions, I would be happy to answer that. I'm sorry that I haven't had the ability to show all of the demos because of the technicalities.